Today we're going to learn how to write a Verilog module that uses the DE1-SoC FPGA push button and slider switches as inputs and LEDs as output. All right, we'll do that with the Quartus software, so you'll be able to program it to your board. So the board layout, if you have the board in front of you or you're looking at the layout here, you can see that we have 10 of these slider switches, 4 push button switches, and then 10 LEDs that we'll be using. There's quite a bit of hardware on this board, but these switches are a good place to get started with our designs. Right. So this all comes from the user manual. Right, the 4 push button switches, if you look at the stencil on the board, you will see that they're key 0, and you really can't see that in this image here, but if you have a board in front of you, key 0, key 1, key 2, key 3, right, to let you know which is which when you're using the board. The way the buttons are wired in, they are at a logic high level when not pressed and a low level when you press them. The buttons have been debounced, and that means that they're appropriate for using as a manual clock input or a reset input in any of our circuits. And we'll be doing that in future tutorials. By debouncing, buttons have mechanical, or they have electrical components as well, but typically all mechanical buttons. When we press a button, the signal doesn't always go exactly from 1 to 0 or 0 to 1. A lot of times with the intermediate contacts of the switch and all in there and the electrical state, will bounce around between 0 and 1 until it settles into a final logic state. And so because of that bouncing around, which usually takes place over just a few milliseconds, could be less than 20 milliseconds, depends on your hardware. It's not something that's observable by the human eye. If you put it on an oscilloscope, you would see that. But this has circuitry in it to have debounce the buttons. Debouncing means is that it's going to wait for a certain amount of time, basically before it settles into that logic state. And actually there's Schmidt trigger circuits in there that handle that for us. So what's important then is that our signals shouldn't be bouncing around. Right. The push buttons themselves, when we work with them in either schematic form, right, or Verilog form, we're going to use the signal names as found in the pin assignment. So they have to match, they're case sensitive, they have to be spelled the same way. So when we want to work with key 0, right, we're going to use the actual bank of keys. When we refer to key 0, this looks like index notation inside the brackets. And we'll see later where we have to actually go ahead and make these different pin assignments. Right. The slide switches, again, there's 10 of them. They're not debounced. Usually we use those as a level sensitive input, as 0 or a 1. When the switch is in the down position, so if you're holding the board, right, down position means it's closest to the edge of the board. That is a logic level low. If you switch it upward or away from the edge of the board, that is a logic high on the switches. Right, the switch names themselves, right, start with switch 0 and go up to switch 9 since there are 10 of them, right? When we work with them individually, they'll be SW0, SW1, etc. We'll see that as we work with them. Right? The LEDs then, there are 10 that we can control. We write to them, so they're always going to be circuit outputs. When we drive the LED pin itself to a logic high, so logic high, logic 1 turns on the LED. When it's driven low, or logic 0, the LED will be turned off. And so if we wire, we're going to wire our switches to the LEDs, and that will be telling us when we have a logic high and a logic low on our different switches. We'll also see when we set up the Quartus environment now that we have to go ahead and specify the device, right, for the actual then chip device that we're using, which is part of the Cyclone 5 family. And we'll be typing in this 5CSEMA 5F31C6 when we do that in Quartus. So actually, let's just go ahead and jump into Quartus now. So let me shut this down. All right, so I've started Quartus. I haven't started a project. I'm going to use the new project wizard, so I can click on new project wizard, or I can also go to file, new project wizard to access it. Right, I'm going to hit next. And let's see, let me save this on my desktop. I'm just going to put it in this folder called tutorial. And I'll probably just name the project tutorial as well too. Empty project, no files. And here's where I'm going to do something a little bit different. Right now I'm going to select the device. So the family has to be Cyclone 5. So Cyclone D, and that's all I've installed on this particular computer. So that is what comes up by default. If I had installed support for other devices like the Cyclone 4, or the Stratix, and so on, then I might have something else coming up and I would be able to select then Cyclone 5 from the drop-down list. So you have to have that Cyclone 5 support installed. And then what we need to do is we want to type in that 5 SCEM. Oh, I get it backwards. CSEMA 5F. And actually, if I make this bigger here, there's a drop down list. And as I'm typing, it's filtering this down. Right. This is the one we want. So I can double click on this, or I can just finish typing here 31C6. And that is the device I want. I can hit next. I've got nothing else to change. So I'm going to hit finish. And so now in the project navigator window under hierarchy, you're going to see that this is our device setting, right? There's my top level design. If you ever wanted to change that, you could double click on that, which brings up then this device window again. And I'm going to cancel that. If you type in the wrong thing or you want to change from one device to another, that's one way of changing your device. All right, let's go ahead and create a new Verilog file. And what we're going to do then is I'm just going to put a little comment here that we're going to demonstrate slide push button switch states and we're going to show states on the LEDs. And I should have made that a multi-line comment since I'm using multiple lines. All right, that's our goal. So we're going to write a Verilog module to do that. Keyword module. I'll just call this maybe board test, or I can call it switch test. All right. Right. And input wire. Right. If I type SW, it's going to think I'm working with the entire bank of switches. And I think what I'm going to do for this example is, let's say we just want to work with 4 switches. So we're going to work with switches 3 down to 0. And when we specify size in the port list, we do a left square bracket 3:0 square bracket SW. And so this says that I want to use switches 3, 2, 1, and 0 on the board. If I wanted all of them, actually, I could say 9 down to 0. I'm going to say 3 down to 0. So you have to have the higher number here, right? You have the colon and the lower number here. If for some reason I only wanted to work with switches 1, 2, and 3, I could do that. But we're going to do 3. And typically we don't say colon, we usually say 3 down to 0. So when we specify the bus width of the switches that we want to use, we have to specify that here in the port list out to the left. Our other input will be the push button. So I'm going to say input wire. And let's just use 2 of the push buttons. So I'm going to say I want to use key 1 and key 0. So I'm going to say 1:0 square bracket key. What I'm saying is that I want to use key 0 and key 1, or 1 down to 0. And then for the outputs, put wire, I'm going to 7 down to 0, LEDR. So when we refer to the LEDs, they're LEDR on this board. And I'm only going to use 8 of them. And to the port list comes our parenthesis and our semicolon. And the module here. All right. And if I want to show my switch state on red LEDs, Right. Now, there are a couple of ways they can do this. I can say assign, and I could say assign to LED R0. And since the red LED 0 is immediately above switch 0, I usually like to connect the LEDs immediately above the switches, so that makes it easy to see when you slide the switch back and forth. So LED R0, I could say assign to that the state of switch 0. All right. So when you work with the individual bits of the bus within the Verilog module, we use that square bracket notation. And here, since I just want to work with LED R0, I'm saying LED R0 here, and I want to assign switch 0 to that. And so if I wanted to do that for all 4 switches, I can say, well, assign to LED R1, switch 1, assign to LED R2, switch 2, assign to LED R3, switch 3. That's a lot of typing. It's fairly clear what I want to do. A faster way to do that is to show switch state on red LEDs. Faster way to do that is I can say I want to assign to the bank of red LEDs 3:0, so 3 down to 0. I want to assign SW switch square bracket 3:0 square bracket. This one line does the same thing as these 4 lines. And what happens is here, right? This is my most significant bit. It's going to assign switch 3 to red LED 3, switch 2 to red LED 2, switch 1 to red LED 1, and switch 0 to red LED 0. Right, so I'll typically write something like this when I have a bank of contiguous signals that I want to assign. I also could have written LEDR 3 down to 0. We also could write this. Because we have defined in our port list the signal SW, and we defined that bus to be 4 bits wide, I could just use that name here and assign it to LEDR 3 down to 0. Now I can't just say LEDR because I've defined LEDR to be a bus width of 8. And so this is only a bus width of 4. This is a bus width of 8. I would get a warning telling me that I'm not connecting to all signals. Right. All right. I tend not to quite do that one. This one hopefully is a little more clear. All right. Either one of these works. I'm going to go ahead and put that one inside of comments to let you know you can't make 2 assignments. I can't have these both active when I go ahead and compile. All right, so now we're showing the states of our slider switches on those red LEDs. Let's go ahead and let's turn off. So I'm going to turn off red LEDs 4 and 5 by grounding them. All right, I've said I want to turn on 8 red LEDs, but I've only got 6 inputs, right? I've got 4 switches and 2 keys. I could enable the other keys, but I'm just going to go ahead and turn these off, right, to show you an example of how you can do that. And so I want to assign to LEDR 5 down to 4, 2-bit binary 0, 0. And what I've just typed is the equivalent of assign to LEDR 4, I can say 5 either way, a 1-bit binary 0, assign LEDR 4, a 1-bit binary 0. Right. When you start working with assigning 0s and 1s or assigning values, so this is an assignment statement, right? We said this is the Verilog continuous assignment statement. It starts with the keyword assign, and it has the assignment operator here. The expression on the right-hand side of the assignment is evaluated and assigned to then target over on the left-hand side of the assignment operator. What this does is the number 2 specifies the size. 2 and then the apostrophe, that's part of the Verilog syntax. So here I'm saying the size of the signal. This is the syntax here, the apostrophe. And then when I type afterward is the base of the number that I'm typing in. So B stands for binary, and that says then the constant value that I'm typing after this is the binary 0, 0. Right, and I type both zeros. I could have said A2, size 2, binary 0. And what this would do is it would interpret whatever, if I just type one number there, that would interpret that as the least significant bit and then 0 fill everything to the left. Right. A lot of times if it's a short sequence, I like to type the entire sequence here. And I have to say that I have a size 2 because over here I'm assigning to a bus width of 2. Right. So your bus width connections always need to match. It needs to know what it needs to wire to what. And what it will do is it will wire the least significant bit right to the least significant bit here, most significant bit to most significant bit. Equivalently, you could have typed these 2 separate assignment statements. But since these are side by side, I just wanted to type the 1. Right. And so this will then turn these LEDs off because we'll always be writing a state of 0 to them. And we saw that a logic low turns off LEDs. If we wanted to turn them on, you could write a logic 1. So binary 1, 1 would keep them both turned on. All right, so you can experiment with those things. But the last thing I want to do is I want to show the button states on red LEDs. Right. And so I'm going to say assign to LED R 7 down to 6, the state of key 1 down to 0. And alternatively, I could have said assigned LEDR 7, key 1, assigned to LEDR equal key 0. All right. Right. So whichever one makes more sense to you, right, use that. So I think I'll leave this one in this form just to show that we can address them individually. All right, that should be all that we need to do before we go ahead and compile this. So I'm going to save it. I have to save the module file, the name of the file with the same name as the module to keep Quartus happy. I also am going to make this, I'm going to go to the file view, I'm going to right click and set that as my top level entity. And I'm just going to go ahead and run analysis and synthesis right now to see if I have any syntax errors. Shouldn't take too long. Okay, good. No syntax errors. Now, another step that we have to take because we want to program this to the board is we now have to make pin assignments. And so those tables that we saw with the pin assignments, let me pop these back up here. Right, we saw this table with the red LED, LEDR1. We actually have to fill in these pin assignments as written. So pin underscore V16 for LEDR1 and so on. But there is a faster way. I'm going to show you a faster way to assign these rather than just type them in all individually. All right, so let me get out of that view and let's just go ahead then. And what we want to do is go to your assignments menu and click on Pin Planner. And what that does is it loads the Pin Planner. And right, when this comes up, what you should see since we've run analysis and synthesis, at the top here, And since we've picked board test as our top level entity, it's going to show us the names of the signals in the port list, right? And it shows them here in alphabetical order. So we've got key 1, key 0, right? LEDR1. So these are the pin names that we've been using. And what we want to do is we need to fill in this location information in order to be able to program the board. Well, a fast way to do that is to use a QSF file. Oh, I love it when things don't want to move from one screen to another. All right, so what I've opened up, and typically we don't open this up. You can find this file on the web for my students. I've given it to them. This file is called DE1-SoC.QSF for Quartus settings file. And if you open it up, looking at, there are a lot. There's settings for every single pin on this board, and they're pretty much in alphabetical order. If we scroll down, past head. So if we scroll down, we get to keys. It's got instructions in here if we import this to set the location assignment to pin _ AA14 for key 0. So we just saw for the red LEDs, right? We saw that that was pin _ V16. And so what we can do is we can just import this file. So I've got this file out on my desktop. Let me just pop open Quartus again. I'm going to close pin planner. I know. Well, Windows, show me both things on the screen, please. Probably because I minimized it. I shouldn't holler at the operating system. I did that. All right. So in order to import pins, again, we go to Assignments, Import Assignments. And then it pops open a window asking for the file name. And so I'm going to click on the 3 dots. So within your project folder, it's always going to create a QSF file. That's not the one you need. So out of my desktop, I've got this file, this DE1-SoC QSF. I'll click on Open, click OK. And nothing magical really happens. And so sometimes you'll see a message pop up saying your pins have been imported. That didn't happen this time. Right. What we want to do is then before we program the board, we have to run a full compilation. And so I'm just going to click on Compile Design and let that start. All right. So it's going to run analysis and synthesis. And what analysis and synthesis has been doing, of course, is taking a look at our schematic, our Verilog code, checking it for any syntax errors, right? And then synthesizing it over to hardware, right? We've taken a look at the hardware that's been synthesized before in the RTL viewer. And now it's going through some other steps, such as the fitter, to decide how to place and route it on the board. Timing analysis, some of this we don't need to let run, but I just go ahead and hit the full compile step. Now compilation takes a little bit longer. As you can see, we've got some warnings popping up here. Number of processors, we could get rid of that warning by going to assignment settings. Under compilation process settings, I could say use all processors. It's still gonna show up for right now. Warnings we're concerned about is we always want to take a look at this one. This says output pins are stuck at VCC or ground. And if we look at this, well, this makes sense. It's telling us that red LED 4 and 5 is stuck at ground. And that makes sense to us because we intentionally said ground that. So we can look at that warning as a designer and say, okay, well, that warning is acceptable because I told it to behave in that way. Right. Now you're going to see some things about pins having incomplete IO assignments. It's going to say that it ignored locations on region assignments. And that's because we've imported, I think there's like about 580 pins. We've imported everything. So what it's telling us is that we've got some pin assignments in there we're not using, which really isn't a big deal for us. What we can do now is we can go back to that pin planner. So if we go back to assignments, pin planner, we open this up. Notice then this is populated now, right? Regions of the board where these pins are. But what we want to make sure is before we program the board, we always want to make sure that the inputs and outputs that we're using in our top level design then have their pin settings. And you can see that it's filled in all these locations for us. Right. And so that's what we're most concerned about, right? The ones in our design always show at the top of the pin planner here, and the board will work correctly if we have the correct pin assignments. Now you could, you can alter that QSF file and take out some of those other pin assignments if you have something that you typically import. For right now, I'm just importing them all. I'm closing that down. And at this point, we've successfully compiled without errors. We could go ahead and program the board, right? We'll do that in another tutorial, but everything now is ready to run on the board. You could download it, program it to the board, play with your switches. Right, we'll do that. We do that as an exercise in one of my classes. And like I said, I'll create another tutorial eventually of filming the board. All right, that's your introduction to how to work with then the LEDs and the push buttons and the switches. Next tutorial, I'll actually show you how to connect them to an instantiation of a Verilog module. All right, hope this helped. Thanks for watching.